here, I should be coming back to the lesson. We start on the lecture notes number 10. And as I said, we are now moving from the linear motion regime into the rotation motion regime. Most of the topics you have seen in the linear motion are ones you have learned in the high school. In here, the rotational motion, the naming of the systems would be slightly different. But many of the concepts that you see in the rotational motion, actually, they are similar. I would not say identical. They are definitely not identical, but they have some similarity, at least in the equation forms, between the linear motion and the rotational motion. So now, let's try to get a quick review on what we have seen in the lesson last Thursday. Mainly, we have focused on the rotational kinematics. Of course, at the very beginning, we have to define what we mean by the rotational motion. And in particular, we are focusing on what we call rigid objects. The rigid objects are the ones that are not changing the shape when they are under the rotation. This is not exactly true, because when you have the rotation, you will see objects that are under a centripetal force. And in order to provide this centripetal force, there must be some stress. There must be some force to pull the objects along the radial direction. And this force actually would cause the deformation of the objects. If you do not, well, it's just like the spring. If you do not extend the spring, there is no force in the spring. So along the spring direction, if you need it to provide a force, then you need to extend it. Just like the case of the atoms in the materials. If you have the shape that is not changed, there is no force among those springs between the atoms, if you like. If you extend them, then there would be an additional force to pull them back together. So if you want to provide a centripetal force, there must be some change in the shape. Of course, if your object is very stiff, very strong, it is not changing the shape very quickly. On the other hand, if it is a pizza or a plasticine that the kids would play for making models when they are young kids, then when you spin them, when you rotate them, the shapes will change, because the atoms are not held together by very strong force. So when they rotate, they keep on changing the shape. And when we talk about the rotation, we would be talking about the rotation about a fixed axis. This is a very important concept. If you want to rotate an object, well, obviously for a wheel, you try to rotate it on the center of the disc or the center of the wheel. But nobody will stop you from, say, spinning a corn. So if I try to spin a corn, I'm not sure if you could see it through the video. Let me try to show it. I just have a corn here. And of course, you are seeing it from the top. So you are not spinning the corn about the center of the plate. So you're not rotating it like this, but you could be spinning like this in the video, as you can see. So the rotation is not only limited to the axis perpendicular to the disc, but it could be along its plane. The axis could be along the plane and passing through the axis of symmetry. There are other scenarios as well. As you will see, all these changes would actually lead to some difference in the motion, in particular the energy associated with the motion, even though they may have the same speed of rotation. So now let us try to make the things simple at the beginning. We only look at the situation when you have the disk that is rotating about its axis of symmetry. That means an axis going perpendicularly to the plane, and well, it is going into the paper for this situation. When it rotates, first let's try to draw a reference line that goes from the center of the rotation to the outside. So this is kind of like the x-axis of the coordinate system. But of course, you do not define the points on the system by just x and y coordinates. Here, we could assign the polar coordinates to any point on the disk. The polar coordinate is defined by the distance from the center to any particular location with a distance r from the center. And theta is the angle extended from the reference line to the line that joins the particular point, say P and here. So all the points on the disk could be uniquely defined by this way, r and theta. When the disk rotates, it will swipe an arc. The length of the arc could be defined mathematically by the equation here, which you probably have learned before. S is the arc length. It is equal to theta times r. And that is the definition of the angle in radian. How is the arc length compared to the radius of the motion? So this angle, which has a unit of radian, is defined in a way different from the angle in the unit of degrees. So you could do the indirect conversion between the angle in radian and the angle in degrees. From now on, when you are doing the rotational motion problems, I would strongly suggest you to think along the unit of radian. Otherwise, you have the things mess up. You have the things that mess up quite easily. And when the object rotates, of course, there would be displacement. But at here, you would have, instead of just linear displacement, there is also angular displacement. I'm talking about the angle extended by the object at the point O, where O is the axis of rotation. So when the object rotates, it swipes through the space, so it leaves a track, and as well as extending an angle, delta theta. Initially, it is theta I, finally, it's theta F. So the delta theta is what we call the angular displacement. Remember, the displacement should always be the final angular position minus the initial angular position. Similarly, the velocity change, any change should be the final value minus the initial value. And for angular motion, clockwise motion is taken as positive value. Well, anti-clockwise motion is taken as positive. Clockwise motion is taken as negative. Kind of like when you move from the left to the right along the x-axis, it is taken as positive. And correspondingly, you will have the angular speed, or if you like, angular velocity, and also the angular acceleration. It is the rate of change of angular displacement and the rate of change of angular speed. Once again, if your object is moving in the anti-clockwise direction, it would have a positive angular speed. And if it is moving more and more quickly in the positive, in the anti-clockwise direction, it will have a positive angular acceleration. That is the idea of the angular speed and the angular acceleration. Units for the angular displacement it should be radian. The unit of angular displacement is radian because you are talking about angles, and we would use a radian for representing the angular displacement. Angular speed, radian per second. Angular velocity, radian per square second. That is the way we use the units in the angular motion. And when we talk about the rotational motion, we first, just like the case of a linear motion, we talk about the kinematics. Kinematics refers to the description of the motion of objects without knowing why. We just have some observations, and we try to link the observations together and create some equations to describe the motion of the object according to the angular displacement, angular speed, angular acceleration, as well as the time. Just like the case of a linear motion, we describe linear displacement, velocity, acceleration, as well as time. So the equations for rotational kinematics, they are listed here. In terms of the equation form, they are highly similar to the set of equations in linear kinematics. As you will see, basically we are changing of course, the symbols. They mean different things. Angular speed is omega, linear speed is v. They are referring to different things, but you see the equation form similarity. Similarly, for the angular displacement and the linear displacement. And the third equation is for situation we don't know the time of motion, but we have the initial and final angular speeds. And finally, it would be for the displacement when we know the initial and the final angular speeds, just like the case of a linear displacement when we know the initial and final velocities and we know the time of the motion. Notice here that on the right-hand side, these equations are valid for constant acceleration. Similarly, equations on the left-hand side, they are for constant angular accelerations. In the lesson on Thursday, we have a look at one problem, and we try to work on it, although we didn't have much time to discuss it after the class. So I have it here. Wow, what is theta? Theta is angular displacement. So at the very beginning, I mentioned it. The angles are measured in radian. Angles are measured in radian. So here you have a disk rotating at 120 radian per second, and it is slowing down with a constant angular acceleration of a magnitude 4 radian per square second. So just like what you did in linear kinematics, you try to firstly write down the terms or the parameters that you know the values are. Here you have the initial angular speed, 120 radian per second, and it is slowing down. So the acceleration is negative 4 radian per second square. Finally, the object will stop. So final angular speed is final angular speed is 0. So here you would like to know the angular displacement. Going back to the set of equations, you will see that the equation we would use should be the third one. You know the final and initial angular speed. You know the acceleration. You do not know the angular displacement. So you go back. Theta or delta theta, it is just a difference in the naming. As long as you get the answer, that should be okay. So here, final angular displacement, initial angular displacement equal over 2 alpha. Of course, it's good that you know the answer. If you do not, the important thing here really is to learn the techniques, because that is really the fundamentals. That is really the fundamentals. And you would be using these equations very often from now on. And in any case, the quiz on Thursday, I just marked the participation without counting the answer marks. Okay. So all the answers are available on the Blackboard in any case. Now, let's come back to the equations at here. Well, here we have some other examples concerning the rotational motion. Maybe I just take a look at one of them at here. You have the object rotating with a constant angular acceleration, 3.5 radian per square second. Angular speed is 2 radian per second at t equals to 0. What is the angular displacement when the wheel rotates? What is the angular displacement of the wheel after 2 seconds, basically? You have alpha, you have t, or delta t, and you know the initial angular speed. So you want to know the displacement. Going back once again to the equations, the equations you need would be the first one. No, sorry, is the second one. The second one, sorry, is the second one. You know the initial speed, angular speed. You know the time, angular acceleration. So you want to find out the angular displacement. And then you try to find out what is the conversion between the angles in radian into degrees and between degrees and number of revolutions. Now, a very different scenario is present at here between linear and rotational motion. In a linear motion, when the x increases, it goes to infinity without coming back. Here, when the object rotates, it comes back to the original position after 2 pi radian or 360 degrees, but doesn't really matter. It just tells you how many revolutions it has completed. You just keep on doing the calculation using whatever angles you calculated. It just tells you how many angles it has, how many revolutions it has wiped through since the initial motion. It doesn't really matter whether it is 5,000 degrees or 5,000 radian per second. It's just corresponding to certain numbers of rotations only. And similarly, in the C, you could calculate the angular speed at the end of the motion. Okay. Now, on the objects that is rotating, you have many particles. Some of them are closer to the axis of rotation. Some of them are further away. So when they are rotating, there is some parameters that are common among them, and that is the angular properties. For example, the angular displacement would be the same for all particles on the disk. When you have the yellow particle rotates by theta, the orange particle would also be rotated by theta. And not even the particles along the same straight line. Some other particles would be rotated by theta as well, as long as they are on the same rotating object. On the other hand, they have different linear displacement because of their distance from the axis of rotation. So the arc length S for yellow particle is theta times R1. Arc length for orange particle is theta times R2. Similarly, we could derive the equations for linear velocity and linear acceleration for the particles. And these linear velocity and linear acceleration, they should, strictly speaking, have the direction that is tangent to the rotational motion. So if you have, in the next slide, actually, in the next slide, you will see that when the object is rotating, the path or the velocity is perpendicular to the radius of motion. So the particle P, as we call it, it is moving tangentially. It is moving along the tangent of the circular arc at this point. So that is why we call this also not just a linear velocity, but the tangential velocity. So when the object is undergoing circular motion, of course, it has an angular speed, but every single particle on the object would have a tangential velocity. That is the velocity of the particle perpendicular to the radius of motion. And similarly, you have the linear acceleration that is equal to r times alpha, which could be obtained by the equation shown at here. Now, this acceleration is tricky. This acceleration is tangential. It is tangential acceleration. What it means is, if you have an object, if you have a disk that is rotating faster and faster, all the particles on the disk should be linearly moving quicker and quicker. And that linear motion is perpendicular to the circular arc. It is perpendicular to the circular arc. So the acceleration in that case is tangential. Sorry. So the acceleration as described by A equals to R times alpha, that would be the tangential acceleration, this part. And at the same time, you have learned in the circular motion, whenever an object performs circular motion, there would be a centripetal acceleration. What is that centripetal acceleration about? Excuse me, could you please turn off the microphone? Right, thank you. So what is that centripetal acceleration about? Okay, when the particle is moving, say at this location, it must be having a velocity v, a tangential velocity v, or an angular velocity omega. No matter what it is, this velocity for the circular motion, for the object to move in a circular path, this linear velocity has to be maintained by a centripetal acceleration. So it is A r, which is the centripetal acceleration, is equal to v t squared divided by r. At the same time, if all the particles are rotating faster and faster, that means the particle it is not kept to move with the same speed that they are moving faster and faster. So for the particle to move faster and faster along the tangential direction, there should be a tangential acceleration. This tangential acceleration is related to the angular acceleration by the equation at here. So that is a very tricky point, actually. The equations that we've seen in the last slide, they are quite straightforward in terms of symbols, but they are actually meaning only the displacement in the linear sense along the circular path, So we are referring to the tangential velocity and the tangential acceleration. Remember that we are having particles that are at fixed location from O. So there is no movement along the radial direction. There's no particle movement along the radial direction. Otherwise, acceleration along the radial direction would not be simply due to centripetal acceleration. There would be some other components which would be extremely complicated. Here, we are talking about only circular motion that may rotate faster and faster. So there would be a angular acceleration, and correspondingly, there is a tangential acceleration equals to r times alpha. Okay. So now let us take a look at some further examples. Here you have a CD, which I think you still have the memory of this device that is used for playing music, and these days we still use them for playing videos. Of course, you have tracks on the CD, which you cannot see, but if you take it under the microscope, they are all there. And the way in which the data on CD are read is by having a sensor, say a sensor placed at different positions on the along the radial direction, and the disk would rotate, but it rotates with the constant tangential speed when it passes through the sensor. So what I mean is you have the disk that keeps on rotating, and the sensor would be moving along a straight line in the CD player. When it comes to a certain location, the disk has to adjust its speed, adjust the angular speed such that when the particles on the disk passes through the sensor, it has the same linear speed. This tangential linear speed is around 1.3 meter per second. So just for your information, to build up the scenario for the example. So here we try to see some parameters for a rotating CD. We try to find out what would be the angular speed in terms of revolution per minute. Now that is something, once again, tricky. In the calculations of the angular properties, for example, angular speed, SI unit should be radian per second. But from time to time, you would be asked to convert it into revolution per minute. So first, let's try to calculate the angular speed in the inner track and the outer track when it is moving with a linear tangential speed of 1.3 meter per second. So in the inner track, omega I, 23 millimeter, so 1.3 meter per second over 23 millimeter, that is 57 radian per second. Converting this into revolution per minute is done in a way shown at here. Now, this is a good example. We'll see. It tells you how the conversion should be done. Idea is you are not changing the physical meaning of the number. You are still having 57 radian per second. So what you could do, you multiply all the things by 1. But this 1 has a very important meaning. This 1 could be a ratio. The ratio of 1 is the ratio of angles, in terms of revolution or in terms of radian. So this one is 1 revolution over 2 pi radian. They are just different ways to represent the same thing. So this is 1. Upper end and the lower end, they are equal physically. But the important thing we will see a little bit later. Similarly, we multiply the same number by 1 again. This one on the upper side, it is 60 seconds. On the lower side is 1 minute. Well, they are obviously the same. But the important thing is we are trying to build up a unit, which at the end, it becomes revolution per minute. So you see, initial unit, it is radian per second. So we have to build up something such that the top becomes revolution and the bottom becomes minute. So we are setting up equation like that. 1 revolution per 2 pi radian. So the unit cancels. Similarly, 57 radian per second. Second is at the bottom. And we multiply by 60 seconds over 1 minute. So the unit of second cancels. At the end, you are left behind the units of revolution per minute. When you do this calculation, you do the operation by multiplying numbers. And you figure out the units separately. So the numbers is 57 divided by 2 pi times 60, and it becomes 540 in terms of number. And the unit becomes, as after the operation, revolution per minute. That is an important point. All the unit conversions are done in a similar way. So later, you do not need to be too worried about converting units. You just multiply all the things by 1. But that number of 1 carries the meaning of equal ratios. Different ways to represent the same thing. And the units have to match with what you are trying to figure out. You do not have to write it down if you can figure it out in your mind. But this is a very clear way to represent the things. In Chinese, we call it 畫公仔畫出腸. We are drawing the guts of the person when we are drawing the picture. So it becomes very, very clear. Okay. And then the next one is the maximum playing time. It's 74 minutes, 33 seconds. How many revolutions does it take? So we assume that when the CD is being played, the sensor would be kept moving from the inside to the outside. So it would be having a constant angular deceleration. Initially, it moves, rotate faster in the center, and then at the edge, it rotates slower. So you can see that the total angular displacement can be calculated in this way. So it is final position minus the initial position, which is equal to 1/2 of the time of playing the CD times the sum of the angular velocities. That is the last equation in a few pages ago. That is the last equation at here. So you could figure out what is the total angular displacement when it is rotating from the center to the outside. And this would correspond to another certain number of revolutions. And what is the corresponding angular acceleration for this to occur? You have the, let me see, you have the time of the revolution, and you have the angular speeds. You have the angular speeds at the beginning and at the end of the motion. So you will find out what should be the corresponding angular acceleration. So these few examples tells you how to operate with the rotational kinematic equations. Of course, we have some other examples that I would post on the tutorial. So you can try on the tutorial questions later. One thing that is good about the rotational motion is that you do not, usually you do not need to resolve components like the case of the linear motion. Okay, so before we talk about the Newton's laws of the rotational motion, first we try to figure out as much parameters as possible in the rotational motion. And once again, we try to figure out the similarity between the rotational motion and the linear motion. In the linear motion, you have the kinetic energy, and that is due to the motion, the linear motion of the objects. So if you have a particle moving at a speed v, that is equal to 1/2 mv squared for the kinetic energy, linear kinetic energy. What about on a rotating object? Now, on a rotating object, you do not have one particle, but you have a whole collection of the particles. But the concept should be similar. Remember, you have a rigid object. So they are just moving along the tangential direction. Go back 2 slides. Or 3, actually. Go back 3 slides. You have the particles moving with a tangential velocity, v. Of course, different particles would be moving with different tangential velocity because they are at different distance from the point O. So every particle have a different linear velocity, but they are somehow linked together because Vi for any particle is equal to Ri times omega. Omega is the angular speed. So let us try to calculate the total kinetic energy of all particles in the rotating object. This is a rigid object, so once again, no motion along radial direction, no speed along the radial direction. That is total rotational kinetic energy. So Kr, it is the sum of kinetic energies, the sum of linear kinetic energies of all particles. What is it? 1/2 MIVI squared. 1/2 MIVI squared. Now, you are having a lot of these terms. For I, counting from 1 to whatever, that correspond to all particles on your rotating object. What do they have in common? 1/2 is common for all of them. And Vi, in a sense, can be represented by Ri times omega. Omega is common among all rotating particles. They are on a rigid object, so they rotate with the same angular speed. So now it becomes 1/2 MI squared omega squared. I correspond to each individual particle. So we are summing up all the kinetic energies of all the particles. Now we are following the equation. So is there anything you are not following so far? You have many particles. You have many particles. Each of them can be considered to be moving linearly. So each of them would be having linear kinetic energy 1/2 MI/VI square. And then you will have VI that is equal to Ri times omega. So this term becomes the kinetic energy of each individual particle expressed in a different form. Then we try to play some trick. We take away 1/2. We take away 1/2. And we take away omega square as well. And what is left behind is a term very tricky. It can be simple, it can be complicated, but what it means is it is the sum of this term, MI/Ri square, for all the particles. It is the sum of Mi times Ri square for all the particles. So, how does this term look like? I'm not saying it is beautiful or not beautiful. I am saying it looks similar or familiar in a certain instance. Remember, we are talking about rotational kinetic energy. Kinetic energy, as we learned before, it is linear kinetic energy, 1/2 mv square. V is the linear speed. Here we have 1/2, a bracket times omega square. Omega is the angular speed, 1/2 times something times omega square, 1/2 times m times v square. They look very similar, although they have very important difference. It is that here m corresponds to the inertia of an object due to linear motion. And what is that? This term, this ugly term. This ugly term, let us try to replace it by a symbol called I. And this I would be the corresponding inertia in the rotational motion. And this I is something we would call the moment of inertia. And that corresponds to the inertia of an object during rotational motion. So there is no particular reason why I has to be equal to this one. It is just that it would facilitate our calculations. And the understanding of the physics can start from here with not a complicated summation of terms, but by a single symbol, I. This I is the inertia in the rotational motion, just like the case of m in the linear motion. And then the things would be much more easy. Now, saying is easy. Real operation can be very difficult. We will start with something more simple. And here, of course, I runs from 1 to whatever number, depends on how many particles you have in the system. And important thing is, it depends on the mass of the particle as well as the distance of that particle from the axis of rotation. So remember these two things. And we are ready to go to the next slide. Here you have a rod. And this rod have 4 particles. And it is, well, kind of a funny rod in the shape of a cross, assuming that the rods have no mass. These rods have no mass, but the particles at the ends of the rod, they have the masses, small m and large m, basically. And we are trying to rotate them. First, we would rotate it in this configuration, assuming that we could. The axis is along one of the rods, and the two larger masses M, they are rotating in a plane of, well, in the XZ plane. If you have some imagination, you could see that the object should be rotating in the XZ plane. So if you look on the top, it is only the mass, the large masses M rotating. In the second configuration, you have the rods that are rotating in the plane that contains both rods. So the axis of rotation is going perpendicular to the cross. So it goes from the top to the bottom. And the rods are rotating in the plane that contains the two rods. Now, we try to figure out the angular, the moment of inertia, as well as the total kinetic energy of the two systems. They have the same mass. All of them contains two small m, two large m. They have the same angular speed about the axis of rotation. But as you'll see, they have different moment of inertia. They have different I, because I is equal to mi times Ri squared. For the first configuration, if the particles are very small, let us assume they are small compared with the dimensions of the rod. So we could assume the distance of the ball from the axis of rotation is 0 for the two small m. For the two large m, that is not. They are at a distance a from the axis of rotation. So what is the total moment of inertia for the first system? M times a squared for the first ball, m times a squared for the second ball, 2m a squared. Total kinetic energy, here you have 1/2 I omega squared, and that is m a squared omega squared. Of course, you could try to figure out the linear kinetic energy of the two large balls. The two small ones, because they are on the axis of rotation, they have no contribution to the kinetic energy because they are too small and they are not moving linearly. So the calculation would give you the same answer, ma squared omega squared. What about the second configuration? In the second configuration, total moment of inertia is due to the small m, which are now at the distance b from the axis. So mb squared, mb squared. The two large balls still at a distance a from the axis. So ma squared, ma squared. So this is the new moment of inertia. Kinetic energy, rotational one, it is a different value. Important message here, even if the objects have the same mass, if they have the same mass, but different configuration of rotation, then the moment of inertia could be changed. That is a very important message to be shown here. And when you change the moment of inertia, all the other properties could be changed as well. Okay. Now, we are not talking about impulse or momentum. Some of you asked on the chat box. We are focusing on rotational motion. So let us not to go back to the linear motion for the time being. We are only focusing on rotational motion. Okay. So the definition of the moment of inertia, just to quickly summarize, it is the sum of the mr squared for all the particles in a rotating object. And the SI unit is, of course, kg times meter squared. And this is the inertia of a rotating object. A very important difference between the inertia in a rotating object and the inertia in a linearly moving object is that mass in the linear motion, it is inherent property. It is intrinsic. It cannot be changed. You have a mass of 50 kg, you cannot change unless you go to the gym and do exercise. But the moment of inertia depends on how you choose the rotational axis. So for the same mass, for the same mass of the object, moment of inertia could change depending on how you choose to rotate it. That is an important point. So, of course, if the things are simple as the last example, everybody would be very happy. You have the moment of inertia easily calculated because you have only 2 balls on a rotating rod. That is not always the case. That is always not the case, actually. When you have a continuous distribution of the mass, for example, a rod, you would have to calculate the moment of inertia in calculus, in integration. Idea is you are chopping up the object into very tiny particles, and then each of them would have certain mass, and each of them would have be a certain distance from the axis of rotation. At the end, you add them up together. This is the idea. In terms of the calculation, that is the job of the calculus. So this is the main idea. And we have a number of examples in the next slides that demonstrates how these ideas could be realized. I would go through them quickly in the next lesson, but we would not test you how to derive them. Instead, we would be using tables like this. We would be giving you exact formulae how to find out the moment of inertia for different objects when they are rotating in different configurations. So the important message once again is the inertia of an object in a rotating system does not depend only on the mass. It depends also on how the mass are distributed. The further away the mass the masses are from the axis of rotation, the stronger would be the moment of inertia. The stronger would be the moment of inertia if the masses are far away from the axis of rotation. So I would stop at here. And